There are forms of destruction that arrive not as impact but as accumulation, not as a single visible event, but as something far quieter, far more patient. Like a steady rain falling on metal for years, so light that no one notices it at first, yet persistent enough to change the structure beneath it. Space, despite its emptiness, has many such processes, and they rarely announce themselves in dramatic ways. One of them carries an almost misleading name: micrometeoroids. The word suggests dust, fragments, particles too small to matter, and on Earth that assumption would be correct, but orbit is not Earth. At orbital velocities, size stops being a useful measure of danger. Energy replaces it. A particle smaller than a grain of sand, moving faster than a rifle bullet, does not behave like dust. It behaves like a projectile, and space is filled with them. Above the planet exists an infrastructure so constant and reliable that modern civilization treats it as background noise. Navigation systems that define position to the meter, communication networks that synchronize continents, atomic time distributed globally to keep financial markets, power grids and data centers aligned down to fractions of a second, weather monitoring, disaster response, aviation, shipping, all of it depends on satellites that never stop moving through an environment we rarely think about once they are launched. These machines survive not because space is gentle, but because engineers design them to endure slow damage. Shields, coatings, redundant systems, safety margins. Everything assumes a certain rate of wear, a predicted environment, a calculated background of impacts that should, in theory, remain stable over time. And for years this assumption appeared reasonable, yet quietly, over more than 2 decades, something began to drift away from those expectations. Not catastrophically, not in a way that triggered alarms, but subtly enough to leave traces in engineering reports that were never meant for storytelling. Solar panels degrading slightly faster than models predicted. Thermal control systems losing efficiency in ways that could not be cleanly explained. Protective layers showing microscopic erosion that appeared uneven, irregular, and difficult to classify. Each case had a plausible explanation. Each report ended without urgency. A manufacturing variance here, an orbital difference there, normal aging with intolerance. This is how slow problems survive scrutiny. They distribute themselves across time, institutions, and disciplines until no single observer feels responsible for the whole picture. The data existed, but it lived fragmented, archived in separate agencies, buried in telemetry logs, locked behind incompatible formats and outdated assumptions. Noise, not signal. At least that was the conclusion for many years. What changed was not the threat itself, but the perspective. The appearance of the comet designated 3I Atlas did not introduce a new danger to Earth. It did something far more unsettling. It forced scientists to look backward. Its trajectory and visibility prompted a re-evaluation of dust flow models, particle distributions, and long-term environmental effects in near-Earth space. To refine those models, researchers reopened old archives, recalibrated past observations, and aligned datasets that had never been compared directly. And when that happened, randomness began to dissolve. When satellite degradation data from different decades, orbits, and missions were placed onto the same temporal framework, the expected flat distribution did not appear. Instead, the anomalies grouped themselves, not dramatically, quietly. In clusters that rose and fell over time, periods where micro-damage rates increased across unrelated systems, then receded, only to return years later under different conditions. Waves, not storms, not spikes. Waves subtle enough to evade intuition, yet persistent enough to leave statistical fingerprints when viewed across a long enough span of history. The implication was not that space had become more dangerous, but that it had never been as uniform as we assumed. that satellites were occasionally passing through thin regions where particle density shifted just enough to matter, invisible corridors, not detectable by human senses but unmistakable to materials exposed long enough. This is where the real risk emerges, because satellites rarely fail from a single event. They fail from accumulation. Each microscopic impact removes a fraction of protection, alters thermal behavior, slightly reduces power margins or sensor accuracy. None of these changes register as failure. They register as aging, and aging is expected until it isn't. When margins erode, systems do not collapse loudly, they drift. Navigation solutions degrade, timing accuracy slips, synchronization weakens. And because modern civilization is built on layers of precise coordination, small orbital errors propagate downward into networks that assume perfection. Communication delays, financial discrepancies, infrastructure vulnerabilities that appear unrelated to space until they are traced back to their origin. This is not a story about a comet striking Earth. It is a story about confidence. Confidence that the environment above our planet is fully mapped. Confidence that slow damage is always predictable. Confidence that if something were truly wrong, it would announce itself clearly. But when facts collected over 20 years finally align, the message is not loud. It does not shout. It does not warn. It simply suggests that we may have mistaken familiarity for understanding. And that raises a quiet, uncomfortable question. What if we didn't miss the danger because it was hidden, but because we trained ourselves to call it normal? To understand why these patterns matter, it helps to slow down and look at what space actually does to moving objects, not in theory, but in practice. Near Earth, space is often imagined as empty, yet it is better described as a sparse ocean of motion. Countless particles move through it continuously, remnants of ancient collisions, cometary debris, and dust shaped by gravity and solar radiation. Most of the time, their presence is statistically harmless. Most of the time, the problem is not their size, it is their speed. Satellites in low and medium Earth orbit travel at velocities that turn even microscopic particles into sources of concentrated energy. When a micrometeoroid strikes a surface at these speeds, it does not simply bounce or settle, it vaporizes on impact, releasing energy that fractures materials on a scale invisible to the naked eye. Over time, those fractures connect, surfaces roughen, coatings thin. Structural assumptions quietly drift away from their original margins. In other words, what looks like dust behaves more like sustained abrasion from a stream of invisible bullets. Engineers have always known this in principle. Spacecraft design includes shielding, layered materials, and conservative safety buffers precisely because slow damage is expected. What makes the past 2 decades unusual is not that micrometeoroid impacts occur, but that their cumulative effect appears uneven across time. The environment seems calm for years, then subtly harsher, then calm again. Not enough to cause immediate failures, but enough to shift long-term performance curves in ways that only become visible after missions end. This is where human intuition struggles. We are comfortable with steady risk. We are far less comfortable with fluctuating risk that never quite announces itself. When degradation is consistent, models adapt. When it is intermittent, it hides inside averages, and averages are reassuring. They smooth away detail. They make uncomfortable variability disappear. Yet when researchers began to examine long-duration telemetry across multiple generations of satellites, the averages stopped telling the full story. Performance losses that should have followed smooth decay instead showed periods of accelerated wear. Not synchronized perfectly, but close enough to raise questions, especially when those periods appeared across different orbital regimes and unrelated platforms. The immediate temptation was to blame local factors: orbit altitude, orientation, material choice, operational profile. Each explanation worked in isolation. Together, They failed to explain why unrelated systems exhibited stress during overlapping windows of time. The possibility that the space environment itself was changing, even slightly, was considered too diffuse to matter. That assumption turned out to be fragile when updated dust distribution models were layered over historical satellite data. Researchers noticed that certain regions near Earth are not uniformly stable. Solar radiation pressure, gravitational resonances, and the subtle influence of passing bodies can redistribute particulate matter in ways that temporarily increase density along specific paths. These regions are not walls or clouds. They are gradients, thin zones where probability shifts just enough to matter over long exposure. In other words, satellites do not need to collide with something large to suffer meaningful damage. They only need to spend enough time passing through a place where the odds are slightly worse than expected. This reframes the problem entirely. The threat is no longer an object but a condition, not a single event but a statistical imbalance that accumulates quietly. And because satellites are designed to survive known averages, they are least prepared for environments that fluctuate just beyond those expectations. What made this realization particularly unsettling was how easily it could have remained hidden. Without long-term archival comparisons, these variations would continue to masquerade as normal aging. Without a reason to revisit old assumptions, the environment would remain falsely categorized as stable. The passage of 3I Atlas did not introduce these corridors, nor did it intensify them. Its value was methodological. It provided a reference point, a moment where attention returned to regions of space that had not been carefully re-examined in years. By aligning observational focus with archival data, it became possible to see what had previously been averaged away. And once seen, the implications extend far beyond individual satellites. Modern orbital infrastructure is increasingly dense. Systems rely on overlapping constellations, synchronized timing, and shared orbital corridors. Small increases in failure rates do not remain isolated, they amplify. Degraded satellites contribute to tracking uncertainty. Uncertainty increases collision risk. Collision risk generates debris. Debris feeds back into the micrometeoroid environment, raising background hazard even further. None of this happens suddenly. It unfolds over years, quietly tightening constraints on systems that assume stability. The uncomfortable reality is that civilization's reliance on orbital precision leaves little tolerance for slow, unmodeled change. A fraction of a % loss in timing accuracy may be manageable. Several fractions distributed unevenly across systems are not. The danger lies not in collapse, but in erosion. In systems that technically function, yet increasingly operate outside the assumptions that made them safe. What makes this difficult to confront is that nothing looks wrong at first glance. Satellites remain in orbit, signals continue to flow, services appear uninterrupted. The degradation hides beneath thresholds designed for a calmer environment, and that brings the focus back to the core problem. If space contains regions where cumulative damage accelerates without warning, and if those regions are only visible through decades of data, then our current confidence rests on incomplete maps. Maps drawn from averages. Maps that assume the future will resemble the smoothest version of the past. The question is no longer whether micrometeoroids matter. The question is whether we have been measuring the right thing at the right scale. Because once slow damage crosses a certain point, recovery becomes expensive, complex, and in some cases, impossible. And the transition from manageable erosion to systemic vulnerability does not announce itself with impact. It arrives quietly, and by the time it is obvious the wave has already passed through. What makes this situation especially difficult is that the space environment does not change in ways that feel intuitive to human observers. There is no visible boundary, no clear transition where one can say a satellite has entered a dangerous region. Instead, conditions shift gradually, influenced by gravitational resonances, solar radiation pressure, and the constant redistribution of fine particulate matter. These forces operate continuously, reshaping near-Earth space on timescales that do not align with mission lifespans or political cycles. For decades, engineers relied on models built around stability, not absolute stillness, but predictable variation. Background level of micrometeoroid impacts that could be averaged, budgeted, and mitigated through design. That approach worked when satellite populations were sparse and operational expectations were modest, but it quietly assumed that the environment itself would remain statistically consistent. The archival data suggests otherwise. When analysts began revisiting historical mission telemetry with updated tools, they noticed that degradation curves did not simply drift downward at steady rates, they bent. In some years, systems aged almost exactly as expected. In others, they accumulated stress more quickly, even when operational profiles remained unchanged. These deviations were small enough to be dismissed individually, yet persistent enough to form patterns when viewed across enough missions. This is where institutional structure played an unintended role. Satellite programs are rarely designed for long-term environmental archaeology. Missions are funded, launched, operated, and retired within defined windows. Once completed, their data is archived, summarized, and often reduced to conclusions that serve immediate engineering goals. Cross-mission synthesis, especially across decades, is rare. It is expensive, slow, and offers little immediate return. As a result, early warning signals remained fragmented. One team saw slightly elevated panel degradation. Another noticed unexplained thermal drift. A third logged surface erosion without a clear source. None of these findings were wrong. They were simply incomplete. In other words, the problem was never the absence of data. It was the absence of continuity. This gap became more significant as orbital infrastructure expanded. Modern constellations place hundreds, sometimes thousands, of satellites into similar altitude bands. They share exposure not only to known debris fields, but to the same subtle environmental gradients. When conditions worsen, they do so collectively, and collective exposure turns minor probabilities into measurable outcomes. A single satellite experiencing accelerated wear can be managed. A fleet experiencing it simultaneously cannot be ignored as easily. The wave-like nature of these effects becomes clearer when plotted against long-term particle distribution simulations. Certain orbital corridors intersect regions where fine debris and micrometeoroid density fluctuates due to gravitational shaping and solar influence. These regions do not remain fixed. They drift, stretch, and thin. Satellites may pass through them repeatedly over months or years without any single traversal standing out as unusual. In other words, exposure is cumulative, but recognition is delayed. This delay has consequences. Protective margins are consumed earlier than planned. Redundancies are called upon sooner. Operational flexibility shrinks quietly. By the time anomalies are noticed, the underlying cause has often moved on, leaving only the effects behind. What makes this especially dangerous is that failure does not arrive evenly. Some satellites degrade faster, others remain stable. From the outside, the system appears healthy. Internally, it becomes uneven, and uneven systems behave unpredictably. This unpredictability matters because modern space infrastructure assumes synchronization. Navigation accuracy depends on consistent timing. Timing depends on stable oscillators. Oscillators depend on thermal and electrical stability. Each layer assumes the one beneath it behaves within known limits. When small deviations accumulate across layers, the assumptions begin to break, and yet nothing explodes. Signals still transmit, positions still resolve, services still function. Until they don't, not suddenly, but inconsistently. Intermittent errors are the hardest to diagnose. They do not repeat on command. They vanish when tested. They leave no obvious fingerprints, and when traced backward, they often end at boundaries between systems, not at a single broken component. This is how slow orbital degradation translates into terrestrial vulnerability, not through dramatic outages, but through reduced resilience, through systems that have less tolerance for stress, less capacity for correction, and fewer options when conditions deviate from the expected. The realization emerging from 2 decades of aligned data is not that space has become hostile. It is that our models of hostility were too narrow. We prepared for collisions and storms. We did not prepare for gradual, uneven shifts that quietly erode reliability. The comet that drew attention to this alignment did not introduce danger. It introduced clarity. It reminded researchers that space is not static, and that averages can be comforting lies when variability matters more than magnitude. This clarity leads to an uncomfortable implication. If these invisible corridors exist, and if they shift over time, then safety is not a fixed property of an orbit. It is a moving condition, one that must be monitored continuously, not assumed indefinitely. And that forces a re-evaluation of how risk is defined in near-Earth space. Not as a question of whether something will hit us, but whether the environment we depend on is quietly changing faster than our expectations. Because when slow damage accumulates unnoticed, the first sign of trouble is rarely a failure. It is surprise, and by the time surprise arrives, the wave has already done its work. The reason this could remain invisible for so long is not because the evidence was hidden, but because the evidence was inconvenient. It challenged a habit that sits at the center of engineering culture, the habit of trusting the average. Averages make the world manageable. They turn chaotic environments into a single number that can be budgeted, mitigated, and signed off. They allow planners to say with confidence that a spacecraft has a certain lifetime in a certain orbit under a certain set of assumptions. But the moment the environment becomes uneven, when risk arrives, in pulses instead of a steady stream, the average stops being a reliable guide. It becomes a lullaby. In other words, the model can be accurate and still be wrong in the only way that matters. Over the last 20 years, the industry built its instincts around visible threats. Large debris objects, catastrophic collisions, intense solar storms, radiation belts. These are dramatic, measurable, and easy to explain to decision makers. They produce clean narratives. An event occurs, damage follows, corrective actions are taken. But micrometeoroid-driven wear does not offer that structure. It rarely produces a single moment that can be pointed to as the cause. It produces a slow drift, a creeping loss of margin that is easy to rationalize away because it looks like normal aging. That psychological resemblance to normal aging is the perfect camouflage. When a solar panel produces slightly less power than expected, the mind immediately reaches for benign explanations. Temperature cycles, a small manufacturing deviation, a difference in attitude control, instrument calibration. Each explanation is plausible. The simplest story wins, especially when the deviation is small and the satellite continues to operate. The incentive is always to close the case quickly, not to open an environmental investigation that might take years and change design assumptions across entire fleets. The deeper issue is that the evidence of micrometeoroid impacts often lives in places most people do not look. It lives in tiny changes in surface properties, in subtle shifts in thermal behavior, in microscopic cratering that does not trigger immediate alarms. Many satellites cannot directly measure the particle environment that is damaging them. They can only measure themselves, how their performance changes over time. That means detection is indirect by default, and indirect detection is always vulnerable to misinterpretation. In other words, satellites can feel the rain, but they cannot always see the clouds. This matters more now because the meaning of small damage has changed. 20 years ago, a satellite degraded a bit faster than predicted, and a mission team adjusted. Perhaps a lifespan shortened slightly. Perhaps a capability degraded at the end of life. The impact was local. But in the era of dense constellations and global dependence, local impacts do not stay local. When many satellites share similar orbital corridors and similar environmental exposure, small shifts in degradation rate can become synchronized stress across an entire system. And synchronized stress is not just an engineering problem. It is a societal one. It's also a political one, though it rarely sounds like politics. The incentives in space development reward launch and deployment more than they reward long-term environmental mapping. The funding structures and timelines are not built to sustain slow, multi-decade investigations into subtle variables. Even when the data exists, the effort required to unify it can be enormous different formats, different telemetry standards, different proprietary barriers, different assumptions embedded into each dataset. And if the conclusion threatens existing economic models, it becomes easier, not harder to ignore. The most dangerous kind of risk is the kind that does not pay you to look at it. So the evidence stayed scattered until the moment it became useful to re-examine it. That is where a well-timed external reference matters, not as a cause, but as a catalyst for attention. When researchers turn their focus toward regions of space relevant to 3I Atlas, the work demanded updated particle models and renewed validation. The comet effectively acted as a forcing function. It made it reasonable to ask questions that had previously seemed too broad, too expensive, too uncertain to pursue. In the process, older datasets stopped being historical footnotes and started becoming part of a continuous record. And once the record became continuous, the wave became visible, not as a perfect sinusoid, not as a clean repeating cycle, but as an unmistakable tendency, clusters of accelerated wear aligning more often than chance would allow, in ways that correlated with particle environment shifts that older models did not adequately capture. That does not mean every anomaly was caused by micrometeoroids. It means micrometeoroids were a larger piece of the puzzle than the system was prepared to admit. In other words, the rain was never the whole story. But it was enough to change the ending. This changes how we should think about the next decade of orbital growth. If the environment above Earth contains moving corridors of elevated particle density, then a constellation's expected lifetime is not just a property of hardware quality. It becomes a property of timing, orbital geometry, and exposure history. Two identical satellites launched 2 years apart into similar orbits could experience meaningfully different cumulative damage, not because one was defective, but because one happened to live through a harsher phase of the environment. That kind of variability is toxic to planning. It creates uneven reliability. Uneven reliability creates uneven service. And uneven service in timing and navigation systems can look like glitches on the surface while quietly eroding trust beneath it. When timing becomes slightly less precise, networks compensate. They add redundancy. They add correction layers. They add error handling. But each layer costs something: latency, complexity, vulnerability to cascading failure. A system can survive a great deal of small degradation before it breaks, but the cost of survival rises and the margin for unforeseen stress shrinks. At some point, the system becomes fragile without realizing it, and fragility is rarely noticed in calm conditions. Fragility is noticed when conditions change suddenly, during disasters, during emergencies, during economic shocks, during moments when humanity depends most on the invisible machinery above its atmosphere. If slow orbital damage reduces resilience, the day we most need reliability becomes the day we discover we have been spending it. This is why the wave matters. It is not about fear of a single event. It is about the quiet mathematics of accumulation applied to systems civilization cannot easily replace. Building new satellites takes time, money, launch capacity, manufacturing stability, international coordination. You do not patch an orbital infrastructure the way you patch software. If a slow environmental shift begins to outpace our assumptions, the correction window closes gradually and then abruptly. And here is the most unsettling part. Even now, the wave may not look like danger, because danger is what we notice when something stops working. The wave is what we notice when everything still works, just with a little less margin than yesterday. To see how a wave of microscopic impacts can turn into something that threatens whole constellations, You have to follow the damage the way engineers do, not as a single crack, but as a sequence of small losses that compound. A micrometeoroid strike does not need to punch a dramatic hole to matter. At orbital speeds, it can create a tiny crater, vaporize surface material, and send a shock through layers that were designed to be smooth, reflective, and thermally stable. The first effect is often cosmetic in appearance and catastrophic in physics. A surface that used to behave predictably begins to behave slightly differently. Heat spreads differently. Light reflects differently. Charge accumulates differently. Those differences are subtle, but on a spacecraft, subtle differences are not noise. They are the beginning of drift. Solar panels are a good example because they are both robust and fragile. They can survive a lot of punishment, and they can also lose performance without giving a clear warning. Microscopic cratering and surface erosion can reduce their efficiency fraction by fraction, and as power margins shrink, the spacecraft does what it must. It prioritizes, it sheds load, it shifts schedules, it reduces peak operations, it leans harder on batteries, it asks thermal systems to do more with less. None of this looks like failure. It looks like operations. It looks like a team making smart adjustments. But every adjustment is paid for with margin, and margin is the only currency that keeps spacecraft healthy when the unexpected arrives. In other words, the damage is not the crater. The damage is what the crater forces the system to do for the rest of its life. Thermal control is even more unforgiving because it is the silent ruler of satellite behavior. A spacecraft is a flying compromise between heat sources and heat sinks. Surfaces are coated and tuned so that radiators reject heat efficiently, so that instruments stay within narrow temperature ranges, so that oscillators and clocks remain stable, so that structural components do not expand and contract unpredictably. Micrometeoroid impacts can roughen radiator surfaces, alter emissivity, and change how heat is radiated into space. A tiny change in thermal behavior can push a component closer to its limits more often, especially during high-load operations or eclipse transitions. The result is not an immediate shutdown. It is accelerated aging, drift in calibration, increased noise in sensors, and a gradual tightening of operational constraints. Now add attitude control and navigation sensors, the systems that tell a satellite where it is and how it is oriented. Star trackers and optical sensors rely on clear optics and stable alignment. Microscopic pitting on a lens or baffle can scatter light just enough to degrade performance, especially when combined with contamination and aging. A spacecraft can compensate for a while, switching modes, applying correction algorithms, relying more heavily on gyroscopes, increasing computation, accepting higher uncertainty. But uncertainty accumulates too. And uncertainty is the beginning of error. Timing systems are the most delicate part of the story, not because they are weak, but because civilization is sensitive. The distribution of precise time underpins navigation, synchronization, and vast networks of automated decision-making. Clocks and oscillators depend on stable environments. They depend on predictable temperature behavior and electrical stability. If a wave of micro-damage reduces thermal margin, if power becomes less stable, if components must work harder or in different regimes, timing accuracy can degrade in ways that remain within specifications until it doesn't. The change might be tiny, but the world that depends on that timing might be less forgiving than the specification assumes. In other words, a satellite can remain within limits, while the system around it becomes less tolerant of any drift at all. This is how a micrometeoroid wave becomes a societal vulnerability without ever creating a headline. It does not break one satellite dramatically. It slightly stresses many satellites quietly. It increases the probability of early retirement. It increases the probability of intermittent faults. It increases the chance that a platform will fail during a period when it is needed most. And once the failure rate shifts, the next stage begins. Not in physics, but in statistics. Because failure in orbit has side effects. A satellite that fails to maneuver becomes an object with reduced predictability. A satellite that loses attitude control becomes harder to track. A satellite that breaks apart rarely, but not never adds fragments into the orbital environment. Even a defunct satellite intact becomes a moving hazard. Each additional object increases the complexity of collision avoidance and tracking, and every avoidance maneuver costs fuel, which shortens lifetimes, which increases turnover, which increases traffic, which increases congestion. This loop is slow, but it is real, and collisions are not gentle. When two objects collide in orbit, they do not produce a single chunk. They can produce thousands of fragments, many of them travelling in similar altitude bands, many of them persisting for years. Those fragments become a new source of impacts, some large enough to be tracked, many too small to be seen reliably, yet large enough to do damage. In a crowded orbital regime, a small increase in failure and collision risk can amplify into a long-term increase in the micrometeoroid-like background that satellites must endure. In other words, the environment can become more abrasive because the system itself is shedding material into it. This is the point where the quiet impact stops being an abstract concept and becomes a feedback mechanism. A wave of small particles accelerates wear. Accelerated wear increases failures. Failures increase debris. Debris increases particle risk. Particle risk accelerates wear further. None of these steps is guaranteed. Each step is probabilistic. But the loop does not require certainty. It only requires a small push sustained over time. This is why corridor-like increases in particle density matter so much. If a region of space becomes slightly harsher for a few months or a few years, it may not look alarming on any single dashboard, but across a constellation, it can shift the baseline just enough to increase turnover and debris generation, nudging the environment toward a more dangerous equilibrium. Once that happens, returning to the old baseline is not automatic. The system can become locked into a higher risk state simply because it has more fragments moving through the same corridors. And this brings the story back to what makes the 20-year alignment so unsettling. It suggests that the waves were not isolated quirks. They were signals of variability we were not mapping with enough resolution. Signals that our models might smooth away, while the real environment continues to shape outcomes in a way that only becomes obvious when damage has already accumulated. This does not mean doom is inevitable. It means awareness is late. Because if you want to reduce a probabilistic risk, you need two things: measurement and time. Measurement tells you where the corridor is. Time allows you to design around it, schedule launches and orbital insertions with it in mind, adjust operational modes during harsher phases, and invest in shielding or redundancy where it actually matters instead of where averages suggest it should. Without measurement, you're guessing. Without time, you're reacting. And reaction in orbit is expensive. What makes the wave so dangerous is that it can be mistaken for background noise until it has already consumed the margin you would need to respond calmly. The moment you notice constellation-level effects is often the moment you realize the environment has been harsher than assumed for longer than you can comfortably accept. Which raises the next question, the one that matters if you care about what happens next rather than what happened before. If the corridor is real, how do you find it in time? And how do you know when you are entering it? Before the first losses are dismissed as normal, finding a corridor like this is not as simple as pointing a telescope at the sky and taking a picture. The particles that matter most are often too small to track individually, yet large enough to cause meaningful damage. They exist in a strange category, invisible to routine surveillance, but physically loud when they strike. That means the usual approach, catalogue, the hazard, predict the conjunction, maneuver away doesn't fully apply. Instead, the environment has to be inferred from indirect evidence, stitched together from sensors that were not originally designed to act as weather stations. In other words, the map is drawn from scars. Some spacecraft carry dedicated impact detectors, plasma instruments, or dust analyzers, but many do not, and even when they do, those measurements tend to be localized in time and orbit. The broader picture comes from aggregation, comparing surface degradation, tracking performance drift, analysing anomalous thermal trends, and correlating those with known dust sources and modelled particle transport. It is a slow science, because it depends on patience and cross-mission consistency, and patience is not something modern infrastructure systems are incentivized to practice. Yet the 20-year alignment suggests that the problem may be measurable if we stop treating it like a mystery and start treating it like a forecastable condition. That requires a shift in thinking, not where is the dangerous object, but when and where does the probability field tighten. The corridor is not a place you avoid once. It is a region you learn to anticipate like a seasonal pattern that returns under certain configurations of solar activity, orbital geometry, and particulate transport. This is where the comet's role as a catalyst becomes more interesting, because it highlights a principle that applies far beyond comets. External attention can force model updates, and model updates can reveal patterns that were previously smoothed away. In the case of 3I Atlas, the effort to refine dust flow assumptions provided a practical excuse to unify data sets and revisit old telemetry. But the implication is broader. We may have been relying on environmental models that were accurate enough for an era of sparse satellites, but insufficient for an era where small percentage shifts translate into large real-world consequences. In other words, the world changed faster than the assumptions did. The good news is that this is not an unsolvable problem. The physics is difficult, but it is not unknowable. Dust and small particle populations can be modelled statistically, and their transport can be simulated under solar and gravitational influences. What has been missing is a dense enough network of measurements to validate and update those models in near real time, and a culture of sharing that treats environmental monitoring as collective infrastructure rather than proprietary advantage, because this is not a problem any single operator can solve alone. A corridor does not respect national boundaries or corporate branding. If it exists, it affects everyone who flies through that orbital band, and the more crowded those bands become, the more the consequences compound. What one constellation sheds into orbit becomes another constellation's hazard. The system becomes shared whether the incentives acknowledge it or not. That is why the most realistic path forward begins with something that sounds boring, but matters more than any dramatic headline: instrumentation, standardization, and data continuity. A handful of well-placed Sentinel platforms designed to measure dust flux and particle populations directly could act as early warning. Not by naming every particle, but by detecting when the statistical environment shifts. In parallel, design standards that treat micro-impact resilience as a first-class requirement, especially for thermal surfaces, optics, and power generation, could reduce the sensitivity of fleets to temporary harsh phases. In other words, you don't need to predict every raindrop. You need to know when the rain becomes heavier than your roof can tolerate. Operationally, there are strategies that become possible once you accept that risk is not constant. Satellites can adjust orientation to reduce exposure of vulnerable surfaces during elevated flux. Fleets can schedule high-demand operations away from harsher periods to preserve thermal margins. Launch and insertion profiles can be planned with long-term exposure history in mind, especially for high-value platforms whose failure would have outsized effects on timing or navigation services. Even modest reductions in exposure during harsh phases can preserve years of margin over the lifetime of a spacecraft. But none of that works if you cannot tell when the harsh phase begins, which brings the story to its quietest and most unsettling point. The environment does not need to become dramatically worse to matter. It only needs to become slightly worse for long enough, while we continue to expand our dependence on orbital precision. If we keep launching constellations under the assumption that the background is stable, then a corridor-like shift becomes a kind of hidden tax. It consumes lifetime, it consumes redundancy, it consumes resilience, and it does so invisibly, until failures appear unexpectedly, and the system responds by accelerating deployment, increasing traffic and tightening the loop. That loop is the closest thing this story has to a villain, not a comet, not a single collision, not a dramatic event, a feedback mechanism that rewards short-term replacement while gradually increasing long-term abrasion. In other words, the risk is not that something happens to us. The risk is that we slowly do it to ourselves. And this is where the 20-year archive stops being a curiosity and starts behaving like a warning. Because the archive implies the corridor has existed before, and it implies we did not recognize it while it was happening. If that is true, then it is possible quietly, without fanfare, that we're already entering another phase now, and the only reason it feels normal is because normal is defined by what continues to function. The most dangerous moment in a slow-changing system is the moment you still believe you have time, because time is what you spend without noticing. And once you notice, you discover you have been spending it for years. So the next step is not to ask whether a comet is dangerous. The next step is to ask what the comet's appearance made us notice, and what else we have been ignoring for the same reason. It didn't fit the story of a dramatic threat. If the wave is real, then the question is not whether it will return. The question is whether we will recognize it early enough to act like it matters, and whether, when the environment shifts again, we will still have enough margin left to respond calmly, or whether we'll do what humans often do when they realize they are late. Move faster. Launch more. Crowd the corridor, and quietly make the next wave worse. There is a reason this story feels almost unfair. The most practical signals of a micrometeoroid wave are not the kind of signals humans instinctively trust. They are not bright flashes or loud alarms. They're gradients in probability, visible only when you zoom out far enough to see patterns across years. And that means the first true detection rarely comes from a single sensor. It comes from correlation one dataset leaning into another until a shape appears, the way a coastline appears only when you step back from the sand. In a perfect world, we would treat near-Earth space like an ecosystem that requires continuous observation, the same way meteorologists treat Earth's atmosphere. We would watch particle flux the way we watch pressure systems, and we would expect it to shift with solar conditions, gravitational geometry, and the slow reshaping of dust populations. But historically, orbital risk was defined by what could be tracked: large objects, measurable conjunctions, known debris fields. The rest was background. It was something you designed against once, early, and then assumed away. In other words, we built a culture of avoiding what we could name and tolerating what we couldn't. The corridor problem lives in what we couldn't name. A zone does not appear as a catalogue entry. It appears as a small uptick in the number of microcraters per square metre, as a slight increase in electrostatic discharges, as a faint change in the reflectivity of a radiator coating, as an unusually fast decline in panel output on otherwise healthy spacecraft. These are not the metrics that drive headlines or board meetings. They are the metrics that appear in end-of-life reports, in anomaly logs, in engineering notes written for people who are too busy to chase ghosts. That is why the archive mattered. It did not reveal a single smoking gun. It revealed consistency. And consistency is what transforms a ghost into an environment. Once you accept that the environment can arrive in waves, you start seeing how fragile our sense of stability really is. Launch cadence becomes a form of exposure management, whether we admit it or not. If fleets are deployed during a harsh phase, they may enter service with less margin than planned, and the consequences can surface years later as premature retirement, uneven performance, and higher operational overhead. If fleets are deployed during a calmer phase, the same hardware may appear more reliable, reinforcing the belief that the average model was correct all along. In other words, success can hide the risk, and failure can look like bad luck. This is also where the story intersects with the uncomfortable mathematics of scale. When you operate a handful of satellites, rare events are rare. When you operate thousands, rare events become routine. A corridor that increases micro-impact probability slightly may barely register for one spacecraft, but across a constellation, it becomes a statistical machine that produces measurable losses. Even if no one's satellite fails dramatically, the fleet can bleed capability. More time spent managing anomalies, more replacements launched earlier than planned, more orbital traffic, more end-of-life disposals executed under tighter constraints. And tighter constraints are where accidents grow. The nightmare scenario is not a single collision that shatters everything. The nightmare scenario is a subtle increase in background abrasion that quietly pushes fleets toward earlier failures, while the orbit becomes more crowded at the same time. That combination increases both the number of objects and the urgency of maneuvering. Operators make more collision avoidance decisions, they burn more fuel, they accept more risk, they retire more satellites, they launch more replacements. Each step is rational in isolation. Together, they accelerate the feedback loop. This is how a slow hazard turns into a system-level trap. It forces the system to respond in ways that make the environment harsher. And this is where the concept of the quiet impact earns its name. It is not one thing hitting us. It is the invisible pressure that shapes our choices until we are living inside the consequences without noticing the transition. The most chilling aspect of all is how late the warning can arrive. Because the corridor does not announce itself on day one, it consumes margin gradually. It appears as small anomalies that remain within tolerances. It creates a story that is always plausible, normal wear, nothing to worry about. And then, in a later year, when enough systems have been nudged toward fragility, the same kind of external stress that would have been manageable before becomes dangerous. A solar storm, a launch delay, a geopolitical disruption that slows replacement cadence, a natural disaster that increases dependence on navigation and communication. Suddenly, what looked like a comfortable buffer is revealed to be thin. In other words, the wave matters most when the world is already under pressure. This reframes the purpose of space safety, away from dramatic prevention and toward boring resilience. It suggests that the highest value work may not be building bigger telescopes to discover the next obvious threat, but building continuous environmental awareness for the threats that never become obvious. Dust flux forecasting, cross-operator data sharing, standardized reporting on micro-impact signatures, design choices that prioritize stable thermal behavior under surface erosion, and perhaps most importantly, an honest admission that the environment can shift in ways our current averages fail to capture. Because if the corridor is moving, then safety is moving too. And the quiet lesson of the 3i Atlas catalyst is that our attention can be redirected, but usually only when something gives us permission to revisit old assumptions. A comet provided that permission once. The risk is believing we will always get such permission in time. The corridor does not need our attention to exist. It exists whether we notice it or not. The only choice we control is whether our maps are updated while we still have margin left to use them. So when people ask, is the comet dangerous? The more honest answer may be, not in the way you think, because the comet is not the threat. It is the mirror. It reflects back a weakness in our model of safety, a weakness that has been quietly present for decades, growing more consequential as we scale our dependence on orbit. And if that is true, then the real suspense of this story is not what the sky will do next, it is what we will do next. Because there are two ways humans respond to subtle warnings. We either slow down and build better measurement, or we speed up and build more replacement capacity. One path turns uncertainty into resilience, the other path turns uncertainty into congestion. And congestion is the one thing you cannot easily undo once it reaches a certain density. Not quickly, not cheaply, not without paying in years. So the question becomes quietly urgent. If the wave returns, will we recognize it early enough to change our behavior? Or will we mistake the first signs for normal wear again, keep expanding, keep tightening the loop, and only understand what happened when the corridor has already consumed the margin we needed to respond calmly? because the cruelest part of slow risk is that it always gives you time, just not in a way you can feel. There is a particular kind of warning that modern civilization is bad at hearing, a warning that arrives as a probability shift instead of a single event. We are trained to react to impact, to interruption, to visible failure. We are not trained to react to a future that becomes slightly more expensive, slightly less reliable, slightly more brittle, one invisible percentage point at a time. The corridor problem lives in that blind spot, because it can change outcomes without producing a moment that feels like the start of anything. If you want to understand why the archive took 20 years to click, consider how evidence becomes believable. A single mission's telemetry can suggest a concern, but it can also be explained away by mission-specific details. A handful of missions can raise questions, but they can still be dismissed as coincidence. What creates belief is repetition across contexts that should not match. Different spacecraft designs, different orbits, different operators, different decades, yet the same kind of subtle acceleration in wear appearing within overlapping windows. That is when the mind is forced to accept that the cause might not be local, that the cause might be environmental. In other words, the pattern becomes obvious only when enough independent stories tell the same quiet lie. Everything is normal, while their numbers drift in the same direction. This is also why the corridor can feel almost philosophical. It's not that space is suddenly hostile, it's that space is alive with dynamics we simplified for convenience. Dust populations are not static. They are continuously reshaped by forces that rarely matter until you scale your dependence on orbit into something global. Solar radiation pressure can shepherd fine particles into gradients. Gravitational resonances can trap or disperse them. Even subtle disturbances spread across years can change where the risk concentrates. The corridor, if it exists, is not a wall. It is a moving tendency, an invisible bias in where damage accumulates faster than expected. And once you accept that, a different kind of question becomes unavoidable. What else have we simplified because it was easier to budget than to map? Because the corridor does not only threaten hardware, it threatens planning. It threatens the assumption that reliability is a property you can purchase once through design and then treat as fixed. If the environment is variable, reliability becomes a moving target. A satellite's lifespan becomes partly a function of when it was launched into the probabilistic weather above Earth. A fleet's stability becomes partly a function of whether its deployment happened during a calmer phase or a harsher one. That makes traditional forecasting feel confident while quietly being incomplete. In other words, you can build excellent machines and still lose time to an environment you mischaracterized. This is where the narrative shifts from technical to personal, because the consequences are not abstract. When navigation is slightly less accurate, aircraft and ships rely more heavily on layered backups, and those backups are not equal everywhere. When timing synchronization becomes slightly noisier, financial and communications networks compensate by adding complexity, and complexity has its own failure modes. When weather and disaster monitoring becomes slightly less resilient, the difference is felt most during the moments when people need clarity, not during the calm. The corridor does not create a single catastrophe. It increases the chance that when the world is stressed, the systems that should be stable become the first to wobble. This is also why the feedback loop matters so much. In a fragile environment, the instinct is to respond with speed, replace faster, deploy more, maintain service. But speed increases traffic, and traffic increases the cost of safe behavior. Collision avoidance becomes more frequent. End-of-life disposal becomes more constrained. Tracking becomes more complex. Small mistakes become more consequential. And all of this happens while the background abrasion continues. The system responds to quiet stress by becoming noisier, more crowded, and therefore less forgiving. In other words, the corridor doesn't need to attack anyone. It only needs to make the system slightly less stable, while the system makes itself slightly more congested. This is the quiet tension at the heart of the story. We are building a civilization that depends on orbital precision the way a body depends on nerves, yet we do not monitor the orbital environment with anything close to the seriousness we reserve for storms, earthquakes, or pandemics. We treat the sky like a stable platform because it usually behaves like one. But stability is not a guarantee. Stability is a relationship between stress and margin. If the stress shifts, the same margin becomes smaller. And if the margin becomes small enough, normal disturbances begin to matter. The most unsettling thing about the 20-year alignment is that it suggests we may have been living through earlier phases of this variability without understanding what we were seeing. The past did not scream, it whispered. It left behind a record of slight deviations dismissed as normal, and only now, with the scale of orbital dependence and the availability of improved modelling, do those whispers line up into a sentence, a calm sentence, a practical sentence, a sentence that is hard to ignore once you hear it. In other words, the danger is not dramatic, but it is real. The environment we depend on may be more variable than our planning culture is willing to admit. And that brings us to the final question this story keeps circling, the one that decides whether it becomes a warning or just an interesting coincidence. If you cannot track every particle and you cannot avoid every corridor, what do you do? Do you treat this as an engineering inconvenience, a small loss in efficiency that can be priced in? Or do you treat it as a signal that the rules of scale have changed, that at constellation density, subtle variability becomes strategic risk? Because once the sky becomes crowded enough, you don't need a catastrophe to lose safety. You only need to lose margin, and margin is lost quietly, one small impact at a time, until the day you discover your system has been running closer to the edge than anyone realized. So the story does not end with a comet. It ends with a choice, whether we build a true environmental forecast for near-Earth space continuous measurement, shared data, models that respect variability, or whether we keep trusting averages, keep replacing faster, keep increasing congestion, and keep calling the first signs of the next wave normal wear until the system can no longer afford that comfort. Because the wave is not what you see when something breaks. The wave is what you see when you finally look back and realize how long it has been shaping everything that still works. If you step back far enough, the corridor idea stops being a niche technical detail and starts looking like a familiar pattern in human history. We tend to build systems that work beautifully inside the conditions we understand, and then we scale those systems until small uncertainties become dominant. At first, nothing breaks. The system even looks stronger because scale creates redundancy and convenience. But scale also multiplies exposure, and exposure is the quiet partner of every risk we thought was acceptable. The corridor is simply one example of that multiplication happening above our heads. The uncomfortable part is that even a well-designed mitigation can fail if it is aimed at the wrong kind of danger. Shielding is not a magic solution if it is optimized for one expected particle distribution, while the true distribution fluctuates in time. Redundancy is not a guarantee if many redundant units share the same exposure history and therefore age in the same direction during the same harsh phase. Replacement capacity is not resilience if replacement itself increases congestion and therefore increases long-term abrasion. These strategies are not useless. They are incomplete when the environment is variable and the system is dense. In other words, the problem is not that we have no defenses. The problem is that we may have been defending against a smoother world than the one we actually live in. That is why the most valuable shift is not a single technology, but a new standard of awareness. Near-Earth space needs something it has never had at the scale it now deserves. A continuous shared environmental baseline that treats dust flux, micro-impact signatures, and particle probability gradients as first-class data. Not as a research curiosity, as infrastructure, the same way weather stations, ocean buoys, and seismic networks exist because societies accepted that nature's variability is not optional. This baseline would not remove risk. It would do something more practical. It would make risk legible. It would tell operators when conditions are drifting toward harsher phases, even if the individual particles remain untrackable. It would turn unknown variability into something that can be managed through scheduling, orientation strategies, and design emphasis. And it would allow planners to stop pretending that the average year is a real place. In other words, the goal is not perfect prediction. The goal is early warning before margins are consumed. There is also a cultural requirement hiding inside the technical one. Shared awareness means shared reporting. It means standardizing how micro-impact evidence is logged and interpreted. It means treating certain anomaly classes not as isolated inconveniences, but as potential environmental indicators. It means encouraging operators to contribute to a common map, even when it is not immediately profitable. That kind of cooperation is difficult in any industry. In a competitive space economy, it can feel almost unnatural. But the alternative is a tragedy of the commons in orbit, because if every operator optimizes only for short-term fleet performance, the long-term environment becomes everyone's problem. The corridor does not care whose satellite is most profitable. Debris does not care who launched first. Abrasion does not respect business models. If the system becomes dense enough, safety becomes a shared property whether we design for it or not. This is the quiet reason the comet matters in the story. Not because it threatens Earth, but because it created a moment where the community was forced to look at the environment with fresh seriousness. It served as a reminder that we do not control the sky. We navigate it. And navigation is only safe when maps are kept current. The danger, as always, is that attention fades. Humans return to what feels urgent and slow risks return to the background. The corridor becomes something a few specialists discuss in journals while the rest of the world accelerates deployment. And the system grows larger while the map remains outdated. In other words, the wave becomes a lesson we learn, then forget, then relearn at higher cost. If you want to know what the future looks like under each path, you can imagine two versions of the same decade. In the first, environmental monitoring becomes routine, and satellites are built and operated with variability in mind. Fleets adjust behavior during harsh phases. New designs prioritize resilience where it matters most, and data sharing slowly becomes a norm because everyone benefits from fewer surprises. Failures still occur, but they are less synchronized, less cascading, less capable of amplifying into debris-driven feedback loops. In the second version, we treat the corridor as a footnote. We keep deploying as if averages are law. When accelerated wear appears, we replace faster. When traffic increases, we accept tighter margins. When anomalies spread, we call them operational noise. The system keeps working right up until the day it doesn't work smoothly anymore, and then the fixes become reactive, expensive, and constrained by the very congestion the system created. Neither version ends with a single dramatic day. One version ends with fewer surprises, the other ends with a world where surprise becomes routine, and that is the quiet definition of fragility. Fragility is not weakness. Fragility is a state where normal stress produces disproportionate consequences. It is the condition where the system can still function, but only as long as nothing unexpected happens. And the corridor, if it is real, is not just a source of wear, it is a source of variability. Variability is what turns strong systems fragile, because it reveals where assumptions were doing the real work. In other words, the corridor is less a threat than a test of whether we can build global dependence on orbit without also building global responsibility for orbit. Because the wave does not need drama to matter, it only needs time, and time is what it already had. 20 years of it, recorded quietly in archives, dismissed as normal until a catalyst forced the pieces to align. The question is what we do with that alignment now, whether we treat it as a warning with a long lead time, or whether we treat it as an interesting story and keep spending margin the way people spend it when they believe tomorrow will resemble yesterday. Because the quiet impact is not the end of anything, it is the beginning of a new kind of accountability, one we can choose to meet early or be forced to meet late. At this point, the story has a temptation that can mislead it. The temptation is to treat the corridor like a mystery that ends when the pattern is recognized. But recognition is only the first step, and in a system as large as near-Earth infrastructure, recognition can arrive long before action becomes real. What matters is whether the pattern changes decisions, whether it reaches the level where designs, operations and policies treat variability as normal rather than as an anomaly to be averaged away. Because the corridor is not a single place you can point to on a map and declare safe or unsafe. Even if models improve, there will still be uncertainty. The environment will still fluctuate. Fine particle populations will still shift under forces that do not care about our schedules. The only stable truth is that the system we've built is sensitive to slow abrasion, and that sensitivity increases as we scale our dependence. In other words, the end of the mystery does not remove the risk. It just removes the excuse to ignore it. There is a practical way to think about this, and it is almost embarrassingly simple. Every spacecraft carries a certain amount of life in the form of margins. Power margin, thermal margin, propellant margin, attitude control margin, redundancy margin. These margins are not luxuries. They are the difference between a satellite that survives unexpected stress and a satellite that becomes a casualty of it. Micrometeoroid waves are dangerous because they spend margins early and unevenly. They do not bankrupt a spacecraft immediately. They quietly move it closer to the point where a normal disturbance becomes fatal. That point is not the same for every satellite. Some platforms are naturally more tolerant. Some orbits experience less exposure. Some designs have surfaces that degrade gracefully. Others have surfaces whose performance collapses after small changes. That diversity is not just an engineering detail. It is how the environment expresses itself as uneven reliability. And uneven reliability creates the kind of confusion that delays response. Operators argue about causes, teams debate whether a trend is real, decision makers wait for certainty that never fully arrives. Meanwhile, the corridor continues doing the one thing it has always done, shifting probabilities. In other words, the wave does not win by being stronger, it wins by being hard to prove quickly. This is why the most effective response is not to wait for perfect proof, but to build systems that benefit from awareness even under uncertainty. If you have sentinel measurements that suggest elevated particle flux, it is rational to adjust orientation of vulnerable surfaces even if you cannot quantify every particle. If you have evidence that certain phases correlate with accelerated wear, it is rational to schedule high-stress operations away from those windows when possible. If you suspect that certain orbital bands exhibit higher variability, it is rational to design for that variability as a baseline rather than as a worst case that probably won't happen. The mistake is not uncertainty. The mistake is using uncertainty as a reason to do nothing, and the deeper mistake is assuming that replacement is always the safer choice. Replacement keeps services running, but it also accelerates the very factors that make orbital safety expensive: launch cadence, congestion, debris probability, tracking complexity. Replacement is a tool. It becomes a trap when it is used as the only strategy, because it normalizes churn. And churn in orbit is not like churn in software. It leaves physical residue. In other words, every shortcut in orbit has a footprint. If you want to see the footprint, you don't need a dramatic collision. You only need to watch how operators behave when margins shrink. They maneuver less. They accept closer conjunction thresholds. They postpone disposals because fuel is tight. They keep dead satellites in orbit longer because the economics are uncomfortable. And each of those decisions, repeated across thousands of platforms, thickens the environment with uncertainty. This is the part of the story that feels like a slow-motion version of a familiar disaster. Not one bad decision, but thousands of reasonable decisions that produce an unreasonable outcome when combined. And that brings us to the quiet role of trust. People trust GPS because it has been reliable. They trust satellite weather because it has been accurate. They trust time synchronization because it has been precise. But trust is built on margins that the public never sees. The public sees the output. The margins are hidden inside engineering tolerances and orbital safety practices. If a wave of microdamage spends those margins early, the system may continue producing the same outputs until the day an external stress hits and the outputs degrade unexpectedly. In other words, the wave doesn't change what you see on a normal day. It changes what happens on the day you need the system most. That is why, in a strange way, this story is not really about space. It is about modern dependence. We have built a world where the most fragile systems are not the ones that look delicate, but the ones that look invisible. The more invisible a system is, the more we assume it will always be there. And the more we assume it will always be there, the less we invest in understanding the conditions that keep it stable. The 20-year alignment is a warning about that habit. It says that slow risks can be present for decades without becoming obvious. It says that a system can continue functioning while quietly becoming less resilient. It says that the real danger is not ignorance, but the comfort that comes from functioning. Because comfort makes us stop listening. And the corridor, if it exists, is the kind of threat that only becomes truly dangerous once we stop listening. So the story ends where it began. Not with an impact, but with accumulation. Not with a dramatic day, but with a long record. And not with a comet as a villain, but with a comet as a catalyst and excuse to look at what was already happening and to finally see the wave in the data we had been calling normal. The question now is not whether the wave is frightening. The question is whether it is actionable. Because action is what separates a slow warning from a slow catastrophe. And in orbit, as on Earth, the price of acting early is almost always smaller than the price of acting late, when the system is already crowded, the margins are already spent, and the only options left are the ones that make the next wave harder to survive. If you want a final image to hold in your mind, don't imagine a rock screaming toward Earth. Imagine something quieter. Imagine a fleet of machines circling the planet like a thin shell of glass, each one doing its job, each one shedding a microscopic bit of itself over time, each one slowly paying a tax to an environment that is never truly empty. That tax is usually predictable enough to live with. The unsettling possibility is that it is not always predictable, and that its fluctuations are the kind you only notice after they have already shaped the outcome. This is why the corridor and the wave feel so strange. They turn the idea of safety into something that isn't a location or a design feature, but a moving relationship. Safety becomes the balance between how much margin you have and how much stress you are accumulating. When stress arrives in waves, the balance can change quietly. A fleet can look healthy while its future is being rewritten in small increments. In other words, the danger is not the moment something fails. The danger is the period before that moment, when the system is still smiling. The reason the 20-year archive matters is that it offers a rare kind of gift, a long-led time. Most technological failures reveal themselves only after they have already produced harm. Here, the harm is still mostly statistical. It is still mostly about probability. That means there is still room to decide what kind of orbital civilization we want to build. One built on constant replacement and accelerating congestion, or one built on awareness, shared monitoring, and designs that expect variability as a baseline. That decision doesn't require perfect certainty. It requires humility. Humility to admit that the average environment is not a guarantee. Humility to accept that models are tools, not comfort blankets. Humility to treat subtle signals as meaningful when scale makes subtlety powerful. Because scale is the quiet amplifier of modern risk. What used to be ignorable becomes consequential. What used to be rare becomes routine. And what used to be background becomes the defining condition of the system. In other words, the wave is not terrifying because it is dramatic. It is terrifying because it is compatible with business as usual. That is the trap. Business as usual continues right through early warning. It continues through the phase where damage looks like normal wear. It continues through the moment margin starts shrinking faster than planned. And it continues even as fleets begin to behave differently, burning fuel earlier, retiring sooner, compensating more aggressively, adding complexity to preserve outputs. The system adapts, it keeps going. And adaptation is easy to confuse with stability, until the day it isn't. By the time a public-facing failure arrives, the corridor has already done its quiet work. The damage has already accumulated, the congestion has already increased, the options have already narrowed. At that point, the conversation becomes loud about regulations, about blame, about urgent replacement, about emergency measures. But the real decision point would have been years earlier, when the archive first suggested the wave was real, and the system still had margin to respond calmly. That is what makes the story feel personal. It is a story about whether we can act before discomfort becomes pain, whether we can choose resilience when everything still appears fine, whether we can treat invisible infrastructure with the respect we usually reserve for things that break visibly. And the comet in this narrative is the perfect symbol of that challenge. 3I Atlas did not threaten Earth in the way people instinctively fear. It threatened something quieter, our habit of ignoring the slow and the subtle. It reminded researchers to look backward, to unify old records, to measure what had been treated as noise. And in doing so, it revealed the possibility that our sky is not just crowded, but dynamic in ways we do not yet map with the seriousness our dependence deserves. In other words, the comet didn't bring the wave, it revealed it. So if you want the cleanest conclusion this story can offer, it is not a warning about impact. It is a warning about normalization, about the way humans can live inside a shifting risk field and call it stable simply because it hasn't hurt them yet. The quiet impact does not ask for belief, it asks for attention. Because attention is what turns archives into forecasts, and forecasts into choices. And choices are what determine whether the next wave becomes a footnote in engineering logs, or the beginning of a new era where orbital systems are no longer assumed to be reliably invisible. The future of space infrastructure will not be decided by a single collision or a single comet. It will be decided by what we do in the calm years, when there is still time to build measurement, still time to share data, still time to design for variability, and still time to keep the corridor from becoming a trap we only recognize once we are already inside it. And if the archive taught us anything, it is that the corridor does not need drama to matter. It only needs time. And time, quietly, is exactly what it has been taking from us all along. If you listen closely to the way engineers talk about risk, you'll hear a word that sounds comforting, but can become dangerous when treated as a substitute for understanding. Nominal. Nominal performance. Nominal degradation. Nominal environment. It means the system is behaving within expectations, but expectations are only as good as the map that created them, and the corridor idea is unsettling precisely because it suggests the map can be smooth, while reality is textured. A nominal year can hide a harsh season, a nominal lifetime can hide an early loss of margin, and a nominal environment can hide a moving probability field that only reveals itself when you finally compare enough histories side by side. This is why the most responsible ending to this story is not a dramatic warning, but a practical shift in what we consider normal to monitor. If near-Earth space contains variability that matters at constellation scale, then the bare minimum for mature orbital infrastructure is an environmental dashboard that treats micro-impact flux as a living condition, not a static parameter. It means building an expectation that every fleet contributes to a shared record, because a shared record is the only way to see slow patterns early. It means designing satellites as if the average is not the real adversary, but the deviation from average that arrives quietly stays just long enough to consume margin, and then leaves you with only the consequences. In other words, resilience begins when you stop treating uncertainty as an annoyance and start treating it as the central variable. There is also a subtle comfort in knowing that this is not a story about helplessness. The corridor may be real and the wave may return, but neither of those statements imply inevitability. They imply responsibility. They imply that the world we built above Earth has reached a point where it needs the same kind of continuous care we already accept for everything else we depend on. We don't build cities and assume they will never experience weather. We don't build power grids and assume demand will always be smooth. We don't build aircraft and assume turbulence will never occur. We build monitoring, we build procedures, we build margins with variability in mind. Orbit deserves the same maturity, because orbit is no longer a frontier we visit occasionally, it is part of the planet's operating system. And once you see it that way, the 20-year archive stops feeling like an eerie coincidence and starts feeling like a field report from a system that has been trying to communicate with us in the only language it has: gradual drift. The drift is not an accusation, it is a measurement, a quiet hint that the environment is richer, more dynamic, and less forgiving of complacency than our planning culture wants it to be. The corridor is not a monster hiding in the dark. It is a reminder that the dark is not empty. So the last thing worth saying is simple, and it's the kind of simple statement that tends to be true in every complex system. The earlier you measure, the cheaper it is to adapt. The longer you wait, the more adaptation turns into replacement. Replacement turns into congestion, and congestion turns into a new baseline of risk that becomes hard to reverse. The wave does not punish you for believing the world is stable. It simply takes advantage of the fact that stability is something you maintain, not something you inherit. And if you ever wonder why a passing comet could matter to this story at all, remember what it actually did. It didn't change the physics of near-Earth space. It changed attention. It created a reason to look back through old records, to line up data that had lived in isolation, to update models that had become comfortable. It gave researchers a moment to see a pattern that would otherwise remain distributed across decades. That is the quiet power of a catalyst. It does not create the truth, it makes the truth visible. The unsettling possibility is that we will not always get catalysts at convenient times. The environment will continue shifting whether we're paying attention or not, and the density of orbital infrastructure will continue increasing because the incentives are strong and the demand is real. That means the most important choice is whether we build a habit of attention that doesn't depend on dramatic moments, but functions as routine maintenance of a shared sky. Because the wave is not a one-time story. If it is real, it is a recurring condition, and recurring conditions are best handled by systems designed to notice them early, not by societies trained to notice them late. If you take one idea from this, let it be this. In the modern world, the most dangerous failures are the ones that begin as normal. They begin as small deviations in graphs no one wants to read. They begin as a little extra wear that can be explained away. They begin as quiet costs that don't feel like threats because nothing has stopped working yet. And then, later, when stress arrives from some other direction, we discover that our invisible infrastructure had been quietly spending its resilience for years. That is what the wave is. It is the slow spending of resilience in a place we treat as stable, because it has been stable enough. And the corridor is the uncomfortable detail that suggests our stability may be more conditional than we like to admit. Which means the real ending is not a warning about the sky. It is a reminder about ourselves, about the way we normalize what continues to function, about the way we confuse continuity with safety, about the way we postpone measurement until we need it. Because the quiet impact doesn't announce itself when it begins. It announces itself later, when the system has less margin than we thought. And by then, the only question left is whether we still have enough time to respond calmly, or whether calm was something we could have afforded only when we were willing to pay attention early. There is one more layer to this story that rarely makes it into public discussions, because it sounds almost too ordinary to be a true threat. The weakest link in complex infrastructure is often not a component, but a dependency. The systems we rely on are not single machines, they are chains. A satellite provides a signal. That signal depends on timing. Timing depends on stable power and thermal conditions. Power depends on panel efficiency and battery health. Thermal conditions depend on surfaces that radiate heat predictably. Those surfaces depend on coatings that remain intact, and those coatings can be changed quietly and permanently by a stream of microscopic impacts that no one can see. The corridor matters because it doesn't target one link. It nudges the whole chain, one fraction at a time, until the chain's tolerance for surprise becomes thinner than the world assumes. In other words, you don't lose reliability all at once, you lose the ability to absorb stress. This is why the right mental model is not risk of failure, but rate of resilience consumption. A satellite can be operating nominally while consuming resilience faster than planned, and a constellation can be delivering service while its collective ability to cope with disruptions is quietly shrinking. That shift doesn't announce itself with a clean error message. It shows up as an increased need for corrections, an increased sensitivity to thermal swings, an increased frequency of small anomalies that never quite repeat the same way twice. It creates a kind of operational fatigue in the system, a steady rise in the number of things that need to be managed, monitored, and patched around. And the more patches you add, the more the system depends on coordination and timing being perfect, even as the underlying margins become less perfect. This is where the wave becomes most dangerous, because it doesn't need to be large to create a coordination problem. It only needs to create unevenness. If some satellites in a fleet age faster, the fleet becomes heterogeneous. Heterogeneity makes prediction harder. Prediction becomes harder at exactly the same time that congestion makes consequences larger. The more crowded the orbit, the less room there is for error. The less room there is for error, the more expensive every anomaly becomes. And when anomalies become expensive, the system's instinct is to move quickly, replace, redeploy, maintain service at all costs. That instinct makes sense locally. But locally sensible behavior can be globally corrosive in shared environments. What makes this particularly unsettling is how calm the early stages look. From the ground, nothing changes. Navigation still works, phones still connect, maps still speak, financial systems still synchronize. The outputs remain smooth because the system is designed to hide its own strain and because operators work constantly to keep it smooth. But smooth output can be a mask. In many critical systems, smooth output is achieved by consuming hidden reserves. When those reserves run low, the system doesn't necessarily collapse, it becomes brittle, and brittleness reveals itself only when the world demands more than usual. A storm on Earth is a useful metaphor, not because it resembles space, but because it reveals how resilience works. Most days, small weaknesses don't matter. A few missing shingles don't change your life. But on the day the wind rises, those missing shingles become the start of a larger failure. The wind doesn't create the weakness, it reveals it. In the same way, a micrometeoroid wave doesn't necessarily produce a visible crisis by itself, it spends margin. Then, when something else happens, an intense solar event, a major launch delay, a supply chain disruption, a geopolitical shock, a natural disaster that increases reliance on precise timing and communications, the spent margin reveals itself as a sudden lack of grace. The system still works, but it works without the comfortable buffer that made it feel effortless. In other words, the corridor is not an apocalypse, it is a stress multiplier. This is also why the 20 years in the story matters so much. It means the pattern isn't speculative in the way people often assume. It means the evidence is already embedded in real hardware histories, in mission logs, in degradation curves, in the quiet paperwork of engineering. The shock is not that something new has appeared. The shock is that something old has become visible as a single shape. And once you accept that, you can't unsee the implication that we may be in the early stages of another wave right now. Not because anyone is hiding it, but because the early stages look exactly like normal. They look like slightly faster wear. They look like small anomalies. They look like nothing. That is the most honest reason this story keeps returning to the same question. Not will something hit us, But are we measuring what matters before it becomes expensive? Because the corridor can't be negotiated with. It can only be anticipated. And anticipation, in complex systems, is not about certainty. It's about building habits that treat weak signals as worthy of attention. It's about building shared baselines that allow slow patterns to be seen early. It's about designing not just for the average environment, but for variability that shifts with time. And if that sounds like an engineering problem, it is, but it's also a maturity problem. Mature infrastructure is infrastructure that assumes conditions will change and builds continuous monitoring into its nature. Immature infrastructure assumes the environment is static and treats monitoring as optional. Orbit used to be a place where optional monitoring was tolerable because the scale was smaller and the consequences were narrower. That era is ending. Not with a bang, but with a quiet transition into dependence. So the most useful way to end this chapter of the story is not with fear, but with a kind of calm seriousness. A corridor of dust and microfragments does not have intentions. It doesn't want anything. It is simply the universe doing what the universe does, moving matter through space under forces that ignore human plans. The only part of this story that involves intention is us. Whether we choose to treat the sky as shared infrastructure that needs continuous care, or whether we keep treating it as a stable platform that will tolerate any scale we impose on it. Because if there is a true cliff at the edge of this narrative, it isn't a comet. It isn't even the wave itself. It's the moment when the world discovers that reliability was never free. It was a margin, and margins once spent are not restored by believing harder.